Our featured presenter for this event is Joseph Ting, a product line manager of Yokogawa's high-frequency instrument. Joseph holds an electrical engineering degree from the University of Texas at Austin and has 15 years of experience in the test and measurement industry, including design and test capacities. Without further ado, I'd like to get started with the seminar by handing it over to Joseph.
Thank you, Sophia, for the introduction, and good day to everybody out there. Thank you for joining us for the next 45 minutes to an hour. This is a very broad topic, data acquisition, and I'm going to try and squeeze as much as we can into this presentation. I'm going to just jump right into it. Please note that if you want a full screen view of the presentation, there is a control on the bottom left-hand corner. All right, as far as the outline, the meat of the presentation, we'll be talking about common noise sources in data acquisition, specifically 7 of the most common types. I would say it's by no means exhaustive, but it's should be pretty thoroughly cover the most common types of noise issues that you see, and maybe some that you weren't aware of, but are present in your system. For each of those noise sources, I'm going to go through and give an example of what it looks like, and then I'm going to show or explain the principle behind the cause of that type of noise, and then finally explain the recommended workaround or how to keep those effects minimized. And before I get into those 7 noise sources at the beginning, I'm going to provide a broad overview of data acquisition. As I said, it is a very deep topic, and I want to make sure that we categorize data acquisition in a way such that I can refer back to certain methods and certain types of architectures through the course of the presentation. As you can see, we'll be covering noises starting with quantization noise, internal A to D noise, power line noise, time skew, and then moving on to aliasing noise, common mode noise, radiated noise, and wrapping up with a couple of examples and discussion about why noise it's important to pay attention to these noise sources and so forth. All right, one quick slide about Yokogawa. I do realize there are many of you out there that are currently using Yokogawa equipment. For those of you who are not, I am part of the Test and Measurement division within Yokogawa Electric Corporation, a Japanese company with 19,000 employees and roughly $4 billion in annual sales revenue. Here in the U.S., our regional headquarters are just outside of Atlanta, Georgia, in a town called Newnan, where we have about 600 employees. All right, speaking of data acquisition, as I said, it's depending on your application, you may look at it by bandwidth. Maybe you are doing low-speed data acquisition, which I consider in the DC to kilohertz type of range, and maybe you're looking at mechanical type of sensors, things like temperature or pressure, physical sensors, or maybe mechanical electronics in the sound and vibration area. Those are quite common. Some people consider data acquisition to apply to higher speed bandwidths as well, kilohertz to megahertz type of application. And again, no matter what type of category you're looking at, the noise is going to be relevant. Certain types of noise will apply to different speeds a little bit more obviously. But within these types of bandwidth, you'll see 2 or 3 types of architectures, instrument architectures. One of which is PC-based internal, which you'll see a lot of vendors on the market that have plug-in modules, either directly inside of a PC or inside of an instrument chassis, with the PC contained in the chassis. And this is a typical low-cost solution that has advantages in that you'll usually have lots of functions on one card, and because the PC is in the instrument, there'll be pretty high bus speed in terms of transfer of the acquired data. On the flip side, this type of architecture is going to be the most sensitive to noise, as we'll discover through the course of this presentation. On the other side, architecturally speaking, there are benchtop type of data acquisition systems which are entirely separate from the computer. They can usually be networked with Ethernet or USB, but again, these would be completely separated, isolated, portable systems that can be used on the bench or in the field. But usually they come at a higher cost. There's a trade-off of fewer channels, hundreds instead of thousands, for example, and it does take up a little bit more space in terms of footprint. And then the combination of these two, which is PC-based external, it would be like a tethered type of solution where you have an external chassis, but the PC is not actually in the chassis. So we'll talk about all three of these types and their sensitivity to noise. Now, in terms of signal types, for the most part, when we talk about data acquisition, people are taking measurements of analog signals. So whether they're directly DC or AC voltages into the instrument, or maybe they are conditioned outputs of a sensor, or sensor outputs that are converted into a voltage. These are analog voltages, and by and large, this presentation is going to apply to analog inputs. I don't want to overlook the fact that data acquisition also includes analog output, and a lot of the noise topics that affect analog input measurements will also apply to analog output. So if you are doing an output of voltage, an analog voltage, maybe an output of a function generator or output of an arbitrary waveform or sweep, keep in mind that these noise sources can also affect those output signals. Data acquisition also applies to digital input signals. We're not going to be covering those in this presentation, but I just wanted to mention that that is an essential part of data acquisition, as well as timing measurements. And noise may or may not be important if you're dealing with digital or timing measurements due to the nature of those signals. But again, if you are getting incorrect measurements on your digital or timing measurements, noise may be a factor. So again, keep that in mind. And then the last way I'm going to sort of classify data acquisition or define the roadmap of how we're heading is by types of applications. And again, depending on the speed and the context of your measurement, the two most common that we see are going to be a low-speed monitoring and trending type of application, where it really behaves sort of like a chart recorder or a plotter that's going to just trend and roll the screen, roll the display of the computer or the instrument from one side of the screen to the other. And this type of low-speed monitoring and recording is especially prevalent in temperature measurements and static DC type of measurements. And you'll often see simple numeric license tag type of views like you see on the bottom left. So certain noises, high-speed noises, high-frequency noises are not going to affect this type of application as much, but we'll get into that a little bit here. On the other side of the spectrum, if you are dealing with high-speed signals, maybe you have a single-shot event. In this case, we have a voltage and a current, and there's a glitch, and we want to capture the events either before or after that glitch. And that's a single activity. Maybe it's a startup condition, maybe it's a shutdown condition, maybe it's a one-time anomaly that occurs overnight. But you could consider that data acquisition in some cases as well. And that's also another type of application that we'll talk about. Now imagine if you have a high-speed event which is repetitive, or a relatively high-speed event which is repetitive, such as if you're dealing with any sort of mechatronics, anything rotating is obviously repetitive, and if you wanted to monitor each cycle of that rotation or each cycle of that waveform over multiple cycles, that type of repetitive waveform monitoring is another type of analog input application. And a sort of related application is a sequential store where you may want to have minimal or zero downtime between these cycles or updates, and that's one type of data acquisition architecture as well. And then another type, the last type, is going to be sort of like a high-speed version of the low-speed trending and monitoring, where you're actually just streaming large, huge amounts, tremendous amounts of data at full speed, perhaps on a high number of channels continuously, and you're really pushing the limits of either the instrument or the PC and streaming it to the hard drive or to the memory or to the display. And we these type of applications in vehicle data acquisition or high energy physics and real-time monitoring tests. So keep those in mind as we talk about the noise sources. And with that, I'm just going to jump straight into the first one. As I mentioned, for each of these noise sources, I'm going to show what it looks like, explain the concept behind it, and then talk about ways to minimize that noise source. The first noise source that we're going to talk about is quantization noise. And I have in this screenshot a grossly exaggerated version of quantization noise, but I do want to show you what it looks like. And essentially, if you see banding on your display either directly or when you're zoomed in vertically, and you'll see discrete steps where it looks like the samples are falling at specific steps or bands vertically, then you may have quantization noise. And this is especially going to affect low voltage measurements, things like thermocouples, ripple measurements where you have again, a small voltage but on top of a DC offset potentially, or high-speed measurements on any voltages. And I say high-speed because there is a trade-off of bit resolution versus frequency. So the higher speed data acquisition types of systems are often 8 bits or in that range, 8 bits, 10 bits, 12 bits. So quantization noise, what causes this effect? Let's take a look. This may be basic to some of you, but I am going to go ahead and explain it. In the decimal system, or base 10, if I say you have one digit to count, then you can count 0 through 9, so you have 10 counts. If I give you 2 digits, then you can count 00 through 99 or 100 counts. And 3 digits gives you 1,000 counts and so on. So the relationship between digits and number of counts or steps is 10 to the number of digits. So 10 to the third gives you 1,000 counts. Well, in the binary system, which is used by all data acquisition systems, which at the heart of every digitizer or data acquisition device is going to be one or several analog to digital converters. Each of these converters is going to have a bit resolution specification. And if it's a 1-bit converter, you can count 0 or 1 in binary, so you have 2 counts. 2 bits gives you the possibility of 0, 0, 0, 1, 1, 0, and 1, 1, so 4 counts. 3 bits gives you 8 counts, and so on. So the relationship between counts and number of bits in the binary system is, as you see there, 2 to the number of bits. So carrying this through to the most common bit resolutions of the hardware we see on the market, an 8-bit system would give you 256 possible counts. 12-bit system would give you 4,096, and 16-bit would give you 65,536 counts. So what do these counts mean is that as you take your measurement between the minimum and maximum voltage scale, then you have to divide that scale, that full scale range, into the available number of steps or counts, which are also called LSB. Here's another view of it. Each data acquisition system, of course, is going to have an A to D converter, which will convert that analog signal into a parallel output of bits. And in this example, if we're measuring between plus and minus 10 volts range, full scale range, then we will have a minimum step size, which is called a least significant bit, LSB, or quanta. And the size of that LSB depends on the number of counts available, which in turn depends on the bit resolution of the device. So an 8-bit system across a plus and minus 10 volt range would correspond to a minimum step size of 78 millivolts, which is, as you can see, is pretty poor. A 12-bit resolution would correspond to a 4 millivolt resolution, and a 16-bit would correspond to a 0.3 millivolt LSB. Now keep in mind that if you're using an oscilloscope, a pure electronic oscilloscope, to make a data acquisition type of measurement, which lots of people do use those. They'll maybe attach a probe, like a differential probe or a voltage probe, passive probe onto a scope. All scopes, almost all scopes, are plus and minus 10 volts using an 8-bit instrument, the minimum amount of voltage scale that you'll be able to resolve is 78 millivolts. And that's the concept of quantization noise. All right, so how do we improve or reduce the effects of quantization noise? Oftentimes when we talk about noise in data acquisition, customers or people's first reaction will be, well, I'll just put a filter on it if you have a noisy signal. And nowadays there's all sorts of software and hardware filters available to do that. Here's an example of, again, pretty dramatic quantization noise. You can see the banding on the yellow trace. And I've applied a low-pass filter at a certain cutoff frequency there. And I think this is I put a very high order, 88th order filter with a very sharp edge. And what you see is the blue trace below is a filtered result. Well, the original trace was actually a pure sine wave. So you can see even with a really good filter, we don't really get a great resolution of the original sine wave. So that's using a filter is not generally a good solution to overcome quantization noise. So what is a good solution? Well, if you'll recall the formula for the LSB is equal to the range divided by the counts. If we want to minimize the size of an LSB, then we either want to reduce the range or increase the counts. How do we do that? Well, the obvious thing is if you're not measuring a large voltage, then reduce the range and let the instrument's amplifier maximize the range around the signal you're measuring. Now, keep in mind this is a linear improvement, so if you went from plus and minus 10 volts to plus and minus 1 volt, that's a 10 times improvement. And again, if you went from plus and minus 1 volt to plus and minus 100 millivolts, that's another 10 times improvement. On the other hand, if you improve the bit resolution or the counts, that is a exponential improvement. So if you go from 8 to 12 bits of instrument resolution, then you've improved your system 8 times. And then if you go from 12 bits to 16 bits, that's 64 times improvement from 8 bits to 16 bits, excuse me. So it is an exponential improvement. Now, keep in mind that I've dramatized the effects of this quantization noise, but even if you don't see it visually like we do in this example, it still exists. So if you're making some sort of analysis or mathematical calculation based on your measurement, the accuracy of your measurement is going to be influenced by this quantization noise. So you really want to have the best raw data going into any analysis, because even if you don't see it, it is going to affect your measurement result. Okay, so one other thing that's sort of related to improving quantization noise is something called AC coupling. Now, AC coupling is something that you see on almost all oscilloscopes, but you don't see it generally in data acquisition. You do see it on some data acquisition devices. So what does AC coupling mean? On the left-hand side, I have a signal with a DC offset and an AC component. Essentially, you can think about AC coupling as a high-pass filter. So what it does is it's going to block the DC component or remove that, zero out that DC offset. And in this example, what it allows me to do is zero out that DC offset and just look at the AC component centered around 0. Why is that beneficial? Well, you can see the trace on the right. By reducing the DC offset and putting that AC signal around 0, now we can reduce the range. So instead of having a plus and minus 2 volt range, maybe we can go down to a plus and minus 15 millivolt range and improve our quantization noise by that factor as well. So keep that in mind. Your instrument may or may not have AC coupling, but if you are making a measurement on the AC component and you want to remove that DC offset. That feature is specifically designed for that purpose. Okay, the next topic we're going to cover is A to D internal noise. And this is actually related to the accuracy spec of the instrument. And as we covered before, every data acquisition device has an internal analog to digital converter. And of course, that converter is not perfect. It is going to have some inaccuracy, which is the biggest components related to the inaccuracies are the nonlinearity of the A to D converter. And it's also related to the programmable gain instrument amplifier block, which is essentially an internal amplifier. And anytime there's an internal amplifier, there may be a gain and or offset error. And because the nature of A to Ds, any sort of board level electronics will be influenced by thermal effects. So depending on if you're maybe running a data acquisition test in the field or in a temperature controlled environment, or even if you've run your instrument pretty hard for a long time, between the first time that you turn it on and 1 hour later, those thermal effects will affect the accuracy of your measurement. So this internal noise is generally specified indirectly through the accuracy specs. Unfortunately, accuracy specifications are not always consistent from manufacturer to manufacturer. The most common method that you'll see in this specification is going to be a percentage of reading plus an offset error. So I've given an example here on the right-hand side. Here you see the accuracy of this instrument, or the internal A to D noise is reflected as plus or minus 0.15% of the reading, which is your gain error, and a 0.5 millivolt error, which is an offset error, and it compensates for or it covers the nonlinearity errors as well. You'll also see some vendors specifying absolute accuracy, signal-to-noise ratio, effective number of bits, so forth. At the end of the day, it shouldn't be this way, but the way that specs are reported for different data acquisition hardware is fairly inconsistent across the board. And the only way to truly discover the relative accuracy of these devices is to compare them side by side. So if you are in the market for a data acquisition device and you are concerned about measurement accuracy, I do encourage you to do side-by-side comparisons on the actual signal using calibrated reference, and to discover which one is going to, in fact, give you the best accuracy under your test conditions. So keep that in mind. The next influence of noise and data acquisition is power line noise. Here's one that I think everybody can relate to at one point or another. And this is called, sometimes it's also called pickup or hum. It's very obvious when you have it, because you'll see a frequency, a ripple frequency at the power line frequency. So here in the U.S., it would be 60 hertz. Other parts of the world, it will be the power line frequency, maybe 50 hertz, or maybe if you're dealing with aircraft, 400 hertz. And sometimes when we deal with, ballasts or fluorescent lights, maybe it's a multiple of the power line frequency, like 120 hertz or something like that. So when we see power line noise, it is quite obvious. So then the question is, well, what causes this, and how can we eliminate it? The cause of it is actually related to something we'll discuss later. It can be conducted or radiated. Most of the times it's radiated, and it's electromagnetic interference. But sometimes it can actually be conducted through the instrument or the sensor itself. But regardless, if you do have power line noise influencing your measurement, one of the best ways to deal with it is by using an integrating A to D converter. And this is especially applicable to those low-speed applications. So if you're doing a low-speed trending or monitoring test, an integrating A to D converter is one that quantizes by time rather than voltage. So sometimes you hear them called sigma deltas or delta sigma converters. And essentially, rather than having a straight 8-bit or 12-bit or 16-bit voltage resolution, it's going to oversample in time, and then plus 1 or minus 1 for each time quanta. Well, being that it can integrate over time, you can set a integration period. And by setting an integration period that is equal to your power line frequency, it creates a notch filter and effectively eliminates those variances because it's integrated over each cycle of the power line frequency. So that's what you see in the bottom right-hand side. That's one way to deal with power line noise. If you don't have control over the device and are not able to change it to one of those, an equivalent method of accomplishing this is by using a moving average filter. So a moving average filter is sort of the same concept, but it's usually applied in firmware or in software. And if you set a moving average with an integration period equal to the power line frequency, then you'll discover it also has a notch filter at that frequency of integration and its multiples or its harmonics. So moving average filter or integrating A to D converters are good ways to deal with power line noise if you can't eliminate it. Now, sometimes you can eliminate power line noise if it's conducted as a form of common mode voltage or if it's radiated as EMI. And we'll talk about those in those noise sections here in a little bit. Okay, the fourth source of noise in data acquisition is time skew. And this is not something that you would traditionally consider noise, electrical noise, but I'm going to call it noise because it has the same effect of noise in the fact that it can corrupt your measurements and it can provide false data and inaccurate data. And the thing that causes time skew here is any data acquisition system that doesn't measure time-aligned data. So in other words, if your data acquisition system has any time shift between one channel and another channel, or if it has a time shift between the plus and minus terminal of the same channel, then that creates time skew. And this time skew is actually one of those little dirty little secrets of the data acquisition industry. It's not really talked about generally, but again, it is real. And if you have a switching or scanning type of measurement device, or if you have a time skew, maybe a single-ended device, a multi-channel single-ended device that actually uses a pseudo-differential measurement, meaning that it measures the positive terminal, then scans and measures the negative terminal, and then subtracts between the two to get a pseudo-differential measurement, there is time skew in your measurement. How will you know if you have this? Again, the principle is that if your block diagram of the instrument that you're using or looking at using uses a multiplexer, maybe that multiplexer has a sample and hold circuit, or maybe it's an external multiplexer, and it has a single A to D converter for a set of channels, then you will be introducing this time skew. It's also called interchannel skew, or it's related to something called the channel clock. On the other hand, a data acquisition system which has independent A to Ds on every channel, has an A to D converter on every channel, is going to typically offer you simultaneous sampling, where the data is going to be time correlated. Of course, the trade-off is cost, and the reason why data acquisition systems are multiplex at all is because it does offer cost savings. In some cases, the time skew is acceptable. And those cases are basically when your scan clock, as you can see in the diagram, is much greater than the channel clock. So in other words, if you're only measuring data at once a second, and your channel clock is 1 microsecond or 1 millisecond, then you can see the time skew has a very, very negligible effect on your overall measurement. But what if your scan clock is only, instead of a million times greater or 1,000 times greater than your channel clock, maybe if it's only 10 times greater, now you may be introducing quite a lot of noise or corruption into your data. So again, keep that in mind, and if you have a device that is pseudo-differential that will be explained in the manual, then be aware that there will be time skew between the plus and minus terminal of the same channel even. Okay. The next topic we're going to talk about is a little bit deeper, but I'll try and cover it quickly. It's called aliasing noise, and this is also referred to as fold-over distortion. And the concept here, is that you have some noise that's introduced when you try and measure a signal that has higher frequency content than you're capable of measuring. So that higher frequency content is going to come back into your measurement and appear as noise. Let's take a look at how and why that happens. In order to understand that, I'm going to refresh everybody's memory here about the time domain and the frequency domain, and the concept that any analog signal can be broken down into sine waves of various amplitudes, frequency, and phase. So this is just your Fourier transform. And if we look in the frequency domain, that time domain signal can be represented as multiple frequency domain components, sine waves, with a maximum frequency component, which we'll call F max. So let's look at an example here. If we are trying to measure this red trace, which is just a simple sine wave, and we use the green dots to take the measurements. In the first example, we're oversampling at 20 times this frequency, the fundamental frequency, or this frequency of the red trace. So if we connect the dots of the green samples, it's no problem to easily recreate that signal. And so that's 20 times oversampling. In the middle example, imagine we've reduced, we only use the oversampling to 5 times, meaning we only have 5 sample points per cycle of the original trace. And if we connect the dots there, you can see it's a little bit jagged, but you can more or less get the original waveform. And in fact, you can get the original waveform perfectly if we were to apply a sort of a curve fit or a filter rather than a connect the dots type of mechanism. So no problem again in the second example. Now, what about the last example? So if we only have 2 samples per period, and we try to recreate this sine wave, well, if we connect the dots, it gives us looks like a triangular wave. And in fact, if we shift the phase of the samples, the green samples, we might end up with a flat line. So we might not be able to recreate this signal very well at all. So the relationship between this frequency that you're trying to measure and the necessary sample speed is in fact 2 times. So this Nyquist or Shannon sampling theorem it just tells us that you need to sample theoretically at least 2 times the highest frequency component in order to accurately recreate that waveform or that frequency component. What happens if we violate that principle, that 2 times oversampling principle? Let's take a look here in the diagrams. I have a time domain representation and then a frequency domain representation of, again, the red original trace and the green sample. Now in this case, we're actually going to hold our sample rate constant, and I'm going to gradually increase the frequency of the original signal. So in the top example, we have 16 samples per second, so well over twice the frequency that we need to measure. And you can see that in the frequency domain, the frequency peak there at 1 hertz, no problem with the green trace or the red trace. Now in the middle signal, if we reduce our sample frequency to 8 hertz, we not reduce the sample frequency. We actually kept the same sample frequency, which was 16 hertz, and half of that is 8 hertz. Well, we've increased the frequency of the red trace to 7 hertz. So 7 hertz is pretty close to 8 hertz now, and you can start to see a little bit of distortion in the time domain. And in the frequency domain, you can also see a spike there, not only at 7 hertz where it should be, but 1 out at 9 hertz. So that's the aliasing effect starting to come into play. What happens if we violate that 2 times oversampling criteria? Which means in the bottom example, if that 16 samples a second of the green trace, which means our Nyquist, or half that sample, Nyquist frequency is still 8 hertz. But now we've increased the red trace to 11 hertz. So the 11 hertz is beyond the maximum 8 hertz that we should be capable of measuring. And so what happens is that 11 hertz gets folded back around 8 hertz, and the difference of 3 hertz gets folded down to 5. So if we were to curve fit the samples from the green trace, you'll find that it is actually a 5 hertz signal. Well, the reality is there's no 5 hertz signal at all in the original red trace. So we've created an artificial alias signal at 5 hertz that really doesn't exist at all. And when you talk about sampling theory, if there is higher frequency content beyond what you're capable of measuring, then you should not see it at all. In other words, we would expect to see in the bottom example a flat line because we're not capable of measuring 11 hertz. We can only measure up to 8 hertz. So that's the concept of aliasing very quickly in a nutshell. Let's look at one more example of aliasing. Now we have a signal, a yellow trace, which has 3 hertz low speed content and a 50 hertz ripple on top of it at 0.2 volts peak to peak and 1 volt peak to peak on the 3 hertz. So in this example, our sample rate is going to be 55 hertz. So 55 hertz is well above 3 hertz, so no problem capturing the low speed signal, but it's not that much higher than 50 hertz. If we do the math here, if we do half of that frequency, it's 27.5 hertz, which is our fold-over frequency or the Nyquist frequency. We'll find that this distorted frequency again is manifest as a low frequency 5 hertz noise. So in fact, if you look at the bottom trace and you connect the yellow dots, then the yellow dots or the yellow are going to be connected as a distorted 3 hertz waveform with some 5 hertz content in it. And in fact, we didn't see anything with the higher speed 50 hertz content. So it just, in the end result, we get a distorted, noisy waveform. And oftentimes people don't realize that what's happening is that higher frequency noise is getting folded back into noise because it's hard to see unless you know that it's happening. This is especially dangerous because in most cases, or in many cases, you don't know what your maximum frequency content is. And in fact, lots of signals have very high frequency harmonics or even infinite harmonics like the sawtooth wave. So if we have a sawtooth wave whose fundamental frequency is one time there in the chart, and we oversample at 20 times, meaning the fold-over frequency is 10 times, you can see all those high-frequency harmonics will get folded over at the 10 times Nyquist frequency and increase the noise floor of the measurement. So that's the real-world effect of aliasing. It increases the noise floor of your measurement. So how do we minimize this effect or deal with it? And this is especially important, by the way, if you're doing any sort of sound or vibration or acoustic measurements. It's especially important to be aware of the effects of aliasing. The correct solution to minimize the effects of aliasing is by using a hardware filter. And I have bolded hardware filter because a software filter is ineffective in dealing with this type of distortion. Once the signal gets acquired past the A to D, the noise is embedded in the signal. There's no way of separating it. So this filter has to be applied before the digitization. And if this type of noise is important to you, if you want to deal with it by using an anti-aliasing filter, you have to check to see if your instrument or your digitizer has one or add one in front of the measurement, in front of the signal before the A to D converter. What is an anti-aliasing filter? It's essentially a hardware filter that is going to preserve the phase characteristics of your signal and provide a very steep roll-off, steep characteristic, and allow you to also set a user-definable filter frequency that's going to be, again, related to your sample rate and indirectly related to that Nyquist fold-over frequency. So hardware filter is, for better or worse, it is the only real solution to dealing with this aliasing problem. Reconstructing the signal. We did talk about this a little bit. If you just connect the dots, you get sort of a decent approximation of the original signal. Most instruments, at least from Yokogawa, will give you the option to do some type of interpolation, display interpolation or data interpolation that can be like a curve fit, or you can do the stair-step method if you like, or you can connect the dots if you turn off the interpolation. Mathematically speaking, if you want to reconstruct the signal, you need to apply an ideal low-pass filter after you've acquired the data with the cutoff frequency equal to the Nyquist frequency. So there's a lot of math behind this concept here, and a lot of, as engineers, it is a little bit impractical to do this. So if you're not deep in, again, into sound vibration applications, more practically speaking, it's better to just oversample, sample at a higher speed rather than dealing with a borderline case and having to mathematically fix your samples. So practically speaking, we recommend an oversampling criteria not of 2 times, but at least 4 times or higher your maximum frequency component. So that's the other thing that you can do in dealing with aliasing. If you don't have a hardware filter, sample faster. Okay, moving on to the next noise topic here, and this is a very important one. In my view, it may be the most important one, definitely one of the most overlooked, and that is common mode noise. So we're going to spend a little bit of time on this topic. Here's what common mode noise looks like. It can manifest itself in a number of ways. It can actually, sometimes you don't see it at all in your measurement. So if we have the original signal with no common mode voltage at the top, it looks as we expect. Maybe we have some common mode voltage on that signal, and we're using an instrument that uses a single-ended or pseudo-differential device. It may cause clipping. So if we have a DC common mode, it may clip your signal, and it may look like the signal in the middle. If you have an isolated digitizer, or if your digitizer provides some sort of common mode rejection, then it will again look sort of like the signal in the third signal, but sometimes it will, or not sometimes, always it will convert that common mode voltage into some amount of noise, and that noise depends on the CMRR, which we'll talk about in a little bit. In the worst case scenario, if you have common mode noise, which is greater than what the digitizer or your data acquisition device is capable of handling, it will damage, and we have seen this in other people's systems. It will actually damage the system where it needs to be repaired or replaced. So this is something to be aware of. Now, I should spend some time and explain to you what the principle of common mode noise is and why it happens and how it happens. Here's a diagram that shows an instrument on the right-hand side and a sensor on the left-hand side. The principle of common mode is very simple. It basically exists when there's a voltage difference between your center ground and your instrument ground. Okay? So in this case, it looks like the sensor is maybe a strain gauge or some kind of Wheatstone bridge, a load cell, and that sensor has a power supply. It's an active sensor. That power supply that's powering the sensor is grounded, and so is your instrument. It's also grounded. If there is a voltage difference between those two grounds, that creates a common mode voltage. Okay? So in other words, it's common because that voltage affects both the positive and the negative input of that channel, of that measurement. Another type of common mode voltage condition that we see is if there is an offset or some kind of electrically active circuit, and you try and take a differential measurement of it. So things like taking a thermocouple measurement, maybe on a motor winding or anything exposed, or transformer or some lighting hardware, something like that, can definitely introduce, or will almost certainly introduce, a common mode voltage. And the thing about common mode voltage is it's not always constant. It can be DC, it can be an AC, or it can be all over the place. So you really never know exactly what that common mode voltage looks like, but you'll know it's there because it will either create noise or potentially damage your instrument. So think about it like if you're going to take a measurement with your hand, your skin. Let's say you want to put your hand on an object to measure the temperature of that object. Well, your skin is going to have, it's going to conduct electricity somewhat. Would you use your hand to measure the temperature of a live electrical circuit? Probably not a good idea. You'd probably want to put on a glove or some kind of insulating device. So the isolation concept is similar. If your sensor has some active circuitry in it, or has a ground which may be floating or separate than your instrument ground, it needs to be aware and handle this common mode voltage, to deal with that common mode voltage. Here's another example, as I mentioned. Maybe if you have a battery is a good example. Here's a fuel cell stack, which may have just 1 volt cells, but they're stacked on top of each other. So the bottom of the fuel cell stack is just 0 to 1 volt. No problem. You can just measure that using a simple voltmeter or oscilloscope. But again, if you wanted to measure that differential voltage, that voltage at the top, it's actually the voltage difference between maybe 399 to 400 volts. And if you take that measurement into a single-ended device or non-isolated device, it could very well damage the device, but because you have 399 volts of common mode voltage. So how do we? This is a related topic, by the way, is grounding problems or ground loops, and sometimes we don't think about ground loops and common mode voltage in the same sentence, but they're actually related to the same effect, and that is to say that there's a potential difference in grounds which causes a current loop. And that current loop, as it drops through resistance, creates voltage variations, which again could be DC, but oftentimes it will be an oscillating voltage. So ground loops, if you've ever dealt with them, are very troublesome to isolate and to deal with. And again, they don't manifest themselves the same way. But the reason they exist is oftentimes because there is a difference between the ground of the instrument and the ground of the sensor or the device you're testing. So how do we deal with this common mode issue? The solution is very straightforward. In fact, almost all Yokogawa equipment that you'll see implements this type of solution, and that is an isolation barrier. Isolation is an electrical isolation, which is going to separate the instrument side and the sensor side. And that isolation can be like a transformer type of isolation or solid-state relay. It can be an optical isolation. But regardless, it separates the effects of a different ground. And it negates negates the common mode voltage. It protects the instrument and it protects the user from these high voltages and the common mode voltages. And it keeps unwanted voltages from affecting your measurement accuracy. So we recommend, if you're working with anything related to power or high currents or exposed electrical components, we highly recommend that you should be considering, and you're seeing noise, we highly recommend that you would be looking at common mode isolation barrier or an instrument that employs one. This isolation can be accomplished in the instrument and through channel isolation, channel to ground isolation. If it's a modular architecture, you may see module to module isolation. You can also accomplish common mode isolation to some extent through using isolated or differential probes and accessories or isolation barriers that are signal conditioners, though that does introduce another stage of calibration and maintenance and system accuracy. So ideally, if it's possible to have the isolation in the data acquisition or in the instrument, that is the best. Now let's talk about this term you may have heard of, common mode rejection ratio. What is CMRR? Well, when we talk about isolation, it's not a simple black and white thing, meaning that if you have isolation from 5 different companies or 5 different instruments, the performance of that isolation will vary dramatically. And the way that we measure that isolation performance is through CMRR, common mode rejection ratio. What that means is it's a ratio of how much of that common mode voltage gets converted to noise. Okay, and that is expressed in decibels. Unfortunately, most of the time that CMRR spec is not part of the standard specifications which are published by the vendor. But believe me, if you ask, those specifications will be made available. So if isolation is an important part of your instrument, if you believe that you are dealing with common modes, then please make that a priority to understand the CMRR performance of your instrument. The typical, let me give you some examples, typical CMRR of an isolated data acquisition system would be around 70 decibels, or the ratio is 1 to 3.2 to the negative 4th. Realistically speaking, that means if you have 100 volts of common mode noise in your signal, that will get converted to 32 millivolts of noise. So that's what that means. The isolation will protect your instrument, but CMRR determines the resulting noise of that isolation barrier. This is a CMRR specification for one of the most popular data acquisition modules from Yokogawa. It's as you can see, the CMRR will vary depending on the input, the frequency of that common mode signal. So anywhere between 10 kilohertz down to DC, this particular module has minus 140 dB, which in the real world, what that translates is to 100 volts of common mode noise, common mode voltage will be converted to 0.01 millivolts of noise. So Yokogawa has one of the best reputations in the industry for isolation performance and for noise performance based on our leadership in power electronics, power meters, and industrial applications. But again, you may want to be, just check the instrument performance of CMRR if you are looking at the isolation spec. Okay, the last topic here I'm going to cover is radiated noise. This is actually, I cover it last, but it's often the one that people think about first when you think about noise. And radiated noise, of course, it means that if you have noise, electrical noise in the air, whether it's through another electronic circuit or maybe you have a motor or a drive or something that's producing a lot of power and releasing that as EMI through the air, which then will get picked up through the antenna. Maybe it's a ground lead, maybe it's an exposed cable of your measurement system and appear in your measurement and corrupt the measurement. So let's talk about EMI for a little bit. Obviously, if you have it, you may be aware of it. If you're in a high power environment, you're probably going to be more sensitive to this type of effect. And everything that's related to reducing EMI, by the way, is related to shielding. So when we talk about shielding, some of this you can handle as an engineer, as a customer, but a lot of this is the responsibility of the manufacturer. And when we talk about shielding, everything is related to this Faraday cage principle. That is that electric field within a closed surface is zero. The same reason why when lightning strikes on an airplane, that everybody inside is protected, because it's an electrically closed surface. So anytime you see a data acquisition board that is not electrically enclosed by metal, then that means it is going to be susceptible to EMI noise. So you will never see a pure exposed board for data acquisition hardware from Yokogawa. Here's an example you can see on the bottom right of some of the shielding that we employ in the module, which is actually has a clear insulation barrier there, but then the metal is insulated. Inside of the hardware, the module itself, you can actually see some optical fiber, and that's part of the isolation barrier. But the EMI shielding is going to be the metal plating, and that's the internal module shielding. External to the module, you should expect some chassis shielding that again accomplishes the same thing. Provides a Faraday cage around the chassis, which should be metal or have an internal metal cage. And same thing if you're building a rack system or a rack and stack system, be aware that you can reduce the effects of EMI by providing a Faraday cage around your rack. So some things, as I mentioned, you can influence. Some things are the responsibility of the manufacturer, but if you are in a situation where you care about EMI, then please pay attention to how the manufacturer accomplishes this shielding. And by all means, in terms of cabling is often the number one culprit in picking up EMI. Avoid ribbon cables at all costs. Avoid unshielded cables, twisted cables. Certain configurations of cable like coaxial and twisted pair are relatively immune to noise, but other types of signals, even a ground clip, like an exposed alligator ground clip on a scope probe, would pick up a lot of EMI under the right conditions. So those are things to be aware of in terms of reducing the noise effects from a cabling perspective. And one thing that we do see in low-speed applications, and the reason why this standard exists, the 4 to 20 milliamp standard, is that the current loop, or the current method of transmitting signals is a lot more noise immune as far as EMI than voltage transmission. That's why it has become the standard in low-speed and industrial applications. So if your signals are low-speed and your application is low-speed, you may want to look at using current transmission rather than voltage transmission for your application. And here's again, to summarize the different types of noises and how they may affect your data acquisition module or hardware. Keep in mind that quantization noise can be overcome by having high-resolution and A to D converter. Common mode noise can be overcome with an isolation barrier. Aliasing noise can be overcome with anti-aliasing filter. Quantization noise can be improved through programmable gain and using that intelligently. Radiated noise can be overcome. Make sure your instrument has, if you're concerned about EMI or radiated noise, it should have a BNC input. Screw terminals are definitely going to be more susceptible to radiated noise. Time skew can be overcome by making sure your instrument has independent channel hardware, and make sure that your data acquisition system also has mechanically and electrically shielded and enclosed hardware as well. We've talked about all these different noise sources. If you're here, obviously you care about it, but I just want to remind you why we think that reducing noise is very important. The number one reason is because it's going to affect your measurement accuracy. And indirectly, if you're doing any sort of analysis, it's going to affect that analysis accuracy. And everybody cares, especially on the R&D side, about getting the most accurate possible measurement. But in addition, reducing noise is important because in the process, it can provide safety in the isolation side for you personally and for your equipment, which we know is a sizable investment in some cases. We also see a trend, at least in North America, with increasing use of mechatronics applications and increasing work in power electronics. So no matter what area you work in, whatever widget that you're working on, you probably focused a little bit more these days on the power electronics component because of demands for sustainable energy and renewable energy. So whether that's an inverter that's part of a home appliance or a hybrid electric motor that's part of a vehicle, or alternative energy source like wind or solar itself, it's always going to involve some high power circuitry that needs to be measured with minimum amount of noise. So that's why this topic is very relevant now, especially. And to wrap this up, I'll give a quick example of fuel cell testing. Here's an equivalent circuit of a fuel cell, and essentially to test the fuel cells, these customers are going to excite the fuel cell by using a load and creating a ripple load. But as they load the fuel cell, they're going to measure the DC, or measure the waveform of that fuel cell. And so, as we discussed, with the fuel cell in particular, we need an isolated measurement. Because this is a ripple on top of a DC offset, the customer is able to use AC and DC coupling. The high resolution is important, as well as hardware filtering, since we're only concerned about the frequency of the ripple itself, and simultaneous sampling to avoid time skew. So not one thing by itself is going to overcome noise. You need to be aware of all the most common ones and strategically tackle them one by one. That's the lesson here. In summary, very quickly, these are the data acquisition products you'll see from Yokogawa. We have two instrument types which are called scope quarters, one which is a more benchtop version with a screen, and one which is a PC-based that lets you automate it or run it from the computer. And we have low-speed data acquisition systems called MX or MW100. And I will put this presentation online so you'll be able to see and look at these details a little bit more clearly. On the oscilloscope side, for higher speed measurements, the scope quarter is also present here, and you can see oscilloscope families anywhere from 20 megahertz all the way to 1.5 gigahertz for those higher frequency measurements. So in summary, hopefully we hit on a little bit of something that was relevant to you. We covered a lot in a short time. Overviewing data acquisition, 7 types of common noise influences. And I just want to say that if you'd like more information or if you have any questions, please do feel free to email me and visit our website, which is tmi.yokogawa.com. We have a section called Technical Library, where you will be able to see this archived webinar and play it back on demand within a couple days. And you'll see other webinars and seminars, as well as application notes and videos. So with that, I thank you, and I'll turn it over to Sophia.
Thank you, Joseph, for a wonderful presentation. We have run out of time for our Q&A section. For everyone that submitted questions, they will be answered via email. Also, if you have not yet answered the poll questions, I would request you to please do so at this time. With that, I'd like to once again thank you all for attending and participating in this online web seminar.